Hello, I'm Rodney Brooks, and I'm a member of the IEEE Robotics and Automation Society, and I'm very pleased to be a co-chair of a new technical committee of that society, the Technical Committee for Robotics Research for Practicality. Now, all researchers in robotics, I think, want their research to be applicable to the real world because robots are part of the real world. And I certainly have spent much of my life doing research in universities, but also deploying robots in the real world through a series of companies. At my companies, I've always made sure that we have PhD level engineers so that they are capable of reading the research papers from universities. Because it's important to know what the latest research results are, and to be able to put them into real robots that are practical, we need to understand them at a deep level. But a lot of what makes a robot practical is not necessarily the things that university researchers are working on currently. So this technical committee is trying to expose some of those issues so that we can get more practical robots more quickly. Let me give you some examples. In my own work with companies, we have built 25 million Roombas, which are in ordinary people's houses. Those people know nothing about robotics. They would not read a manual if we included a manual. So the robot just has to work when you get it out of the box. It has to adapt to the situation in the home. When a research team at a university is demonstrating some new concept, things are a little different. They can have the team of graduate students set up the environment to show off the technical achievement as best as possible. But in order to do that, the people, the students, the professors, have to do a lot of work to make sure all the details around that are set up correctly. In the real world, in real people's homes, there's no one to do that. Likewise, at iRobot, one of my companies, we had 6,500 robots in Afghanistan and Iraq dealing with roadside bombs. So when there was a bomb, the robots would go with some teleop and with some intelligence and try to defuse the bombs, and sometimes the bombs would blow up and the robots would be destroyed. But the point was that these robots were operated by Army personnel who had no training in robotics. They didn't know anything about coordinate transforms or quaternions or all the sorts of things robotics engineers like to talk about. They just had to make it work in very dangerous situations. So that meant that the robots had to have a lot of capabilities built in which were beyond what was just in some of the research papers, so that as soon as they were switched on and they sensed their environment, they could set the parameters correctly so that everything would work. It wasn't like a lab demo with a video running. Because we'd had those robots operating for 9 years in the field, in 2011, when the great tsunami disaster hit Japan and then hit the Fukushima Daiichi power plant, our robots were able to be deployed in Daiichi, in Fukushima, very soon afterwards, and were able to be used in part of the shutdown of the plant, and then a lot of understanding of what was going on in the very high radiation areas. If we'd had just robots straight out of the lab, they probably would not have been able to be used because they would have required too much setup. So I think the big difference is, for practicality, is that the robot has to be able to do everything in a new situation. That means that at the moment, it can't do much. It has to do everything of not much. And the real challenge, I think, for robotics in the future is that researchers think about the practicality. So when they come up with something very clever, very innovative, they think about all the other parts around that which are necessary for a robot to be deployable without the research team there. In a more recent company, Rethink Robotics, we were putting collaborative robots in factories all over the world. And our big idea was that we didn't want to have to use integrators. Most industrial robots today have an integration company come in, write the code, figure out where everything's going to go, decide what parts of the environment are stable, what parts where things will move. They're experts at computer vision, if it's a computer vision system, so they can set the computer vision system up with the right lighting, etc. We wanted our robots to be deployable by ordinary factory workers who knew nothing about automation. That meant the vision system just had to work in any lighting condition and make it very practical. So great new algorithms being developed by the research community, very important to feed in, but we had to choose just the ones that were robust enough and were adaptable enough to varying lighting conditions to be used. So practicality is a little different from research. Research is incredibly important, but putting the whole structure around it so that the algorithm, the actuator, whatever it is able to operate in the real world without the research team there, means you have to solve a lot of other problems. Sometimes they're not so interesting from a research point of view, but they can be very satisfying in getting your key research results out into the community and out into real robots doing real things. For me, one of the proudest things in my life is that we were able to help in Fukushima, that our robots were practical enough to make a difference. And I hope that all researchers will get some sort of feeling like that in their life, where something that they have done makes a real difference in the world. But we need practical robots to do that.